Okay, we will do a few more examples from 1-4, continuity, and find the continuity of stuff, and removable continuity. So, let's take a look at, we finished up with number 8. It said find the limit, and then some of those other ones, I guess we could look at finding the limit on some more of those.
I know 15, we could do 16, it's not part of the homework or whatever, but it's not, I don't know if it's just the delta part that I like messes with my brain, or if it's like the entire problem itself that I'm
Yeah, so like on 15, you can't just plug in for delta x because you have delta x in the denominator.
yeah.
Like on that, and the same is true like on 16. So like on 15, because that's a review from, although it's not review of the delta x thing, but it is review approaches 0 from the left-hand side, it said, on 15, I believe.
Yes.
Okay, so what it is a review, though, is a complex fraction. And a complex fraction means a fraction over a fraction. And so whatever x over delta x. So if you initially just got to plug in 0, here it works fine, here it doesn't work. And so you can't just plug in 0, so you have to do some sort of manipulation. You could think about this like, oh, maybe the conjugate of this, but usually the conjugate thing deals with radicals. We did the conjugate on the top multiplied to the bottom. That was with radicals. So here, this is just a complex fraction. This is over 1. So you're going to keep it, flip it, switch it. Use the phrase. So, you're going to just divide this by this. And so, and keep it, switch it, flip it is simply this. And
Multiply it by, like,
divided
1
by
over
7 11ths or whatever it is. You keep this, you switch this, and you flip this. So here, this one, you could just rewrite. So okay, I'm going to take this whole quantity and divide it by this, so it's going to be multiplied by
1 over.
1 over delta x. Now it's still of no value to you yet, because if you plug in 0 here, excuse me, you're going to end up with 0. So you can't do it yet. So, but that would be a start, and then you could look at, I guess one thing you could do is before that, you could find a common denominator between those, or just distribute that in, and then try to simplify from there. So that's one option. Maybe do a common denominator here before you distribute that in, because it'll make it a little more complex. So what would our, just working inside the fraction, what's our common denominator going to be?
X squared plus x delta x.
Yeah, so you need to multiply this side by
Oh, yeah.
x over x, right? So, but yeah, so it's going to be x times x plus delta x. So it'll be x minus x plus delta x. So our multiplying this side by x over x, multiplying this side by x plus delta x over x plus delta x. And then this whole thing is still times 1 over delta x. Then here, what do you get on top there?
Just delta x.
Yeah, just delta x. And then we're like, aha! And you're not aha, but you should.
Yeah.
Should be aha.
Aha.
So what happens to the delta x's?
Cancel.
Yeah, they cancel there. That and that cancels, and then we can go from there. So that's how you work with that one. Piecewise functions, like on 17, if we take a look at 17, and 17, so piecewise functions, When you're looking for limits, it says, okay, the limit as x approaches 3 negative f of x, and then it's x plus 2 over 2, 12 minus 2x over 3, comma, comma, and x is less than or equal to 3, x is greater than 3. So it's approaching 3, this is number 17, it's approaching 3 from which side? Number 17, I have it written up there, so it's from the
Right.
left to the right.
Right.
Approaching 3 from the
Left, sorry.
left, yep.
I gotta get my fingers up.
Yeah, no problem. 3 negative, so it's coming at like 2.999. So if that's the case, you have to look at where the domain is, and they're going to say, okay, if it's approaching from like 2.999, is it going to be this upper one I'm looking at or the lower one I'm looking at? Upper one, right? Because anything less than or equal to 3. If it is approaching 3 from the right-hand side, right, then it would be like 3.0000001. Well, that's anything greater than 3. So then you look at the bottom one. So all you do is say, okay, I'm just going to look up here and plug in 3. What do you get when you plug in 3? 5 halves, yeah. So 3.02 is equal to 5 halves. So that's what you do when you look at those piecewise function ones. Okay? Then I think we could let's take a look at 23. That's we talked about this notation, but we'll review it. Limit as x approaches 4 from the left-hand side, right? 4 negative, so then it's parentheses 5 double bar x double bar minus 7. And I think that double bar may actually have some bracket stuff on it, possibly.
Yes.
No. But something, right? So what's that? Yeah, it's a double bracket, what's the double bracket mean?
The greatest integer? Or
Yeah, greatest integer function. The greatest integer function, you recall, which way does it round, up or down?
Down.
Down, yeah, greatest integer rounds down. Opposite of what you think. Unless it's a ceiling defined like that. Yeah. So you're gonna round down. So in this case, they just want you to plug in a value less than 4, right? So 3.9. Where does 3.9 round to? 3. Yep. So then you say, okay, I'm plugging in some bracket 3.9, but greatest integer function says 3.9. That value turns into 3. So it goes to the integer, and then 15 minus 7, so you get out 8. Okay? So that's how you do something like that. And then, if we take a look at, the continuity of the function, like on 28, if you look at 28, it just says discuss the continuity. So like on 28, I'll write this up here. The graph of it is kind of sloppy. Okay, something that looks like that on 28. So when they say discuss the continuity, you would say, okay, it is discontinuous, because you can just visually see, right? It's not continuous. There's an open circle here. So it's not continuous, and it has discontinuity at -1. And then you can discuss this because f of -1 is not defined. Now the thing is that you remember there's 3 parts to continuity. One of them is the limit exists. Does the limit exist here at -1?
Yes.
Yeah, because it's going to that value infinitely close. So we say the limit exists. So, but f of c is defined is one of the things that we have to check off our list. And if you say f of -1, there's nothing there, therefore it is undefined. Now, if you had here, all of a sudden, this is, okay,
It's defined,
This-
but it's not. It's
Yep.
saying,
f of -1 is defined. The limit as x approaches -1 is there, whatever the numbers are. But, what did you were saying? They're,
no, they're the same.
yeah, they're not the same, right? So these don't equal each other, therefore the third rule is broken, therefore there's no continuity. So third rule is broken. The point of this is not to visually say, yeah, it doesn't exist. It's like, well, I already knew that. Or it's not to
But
visually
why?
look and say it's not continuous. I keep saying not continuity. It's not continuous. Yeah, we see that, but why? Okay, because it's not defined. This one, for that example, I was saying it is defined, there is a limit, but they don't equal. I added another thing on. Okay, so then that transitions us up to number like, let's take a look at 34, let's say. You guys have to do 3 through 84 every third. So 33 is a piecewise function, but let's see if we can make sense of, discuss the continuity of the function on the closed interval. Okay, closed interval, remember what that means is, it's like 34 here. What is closed? Well, interval, there's interval, open interval, closed interval. If I said 2 to 5, and then I said 2 to 5. So here's option A, option B. Which one's closed?
B.
B. Because it includes the 2 and 5. Yeah, closed circle. So open interval, closed interval. So there's your interval piece. So then it just, so when I say closed interval, that's what you're referring to. You can see there on all of those 31 through 34 options, they're all bracketed. Therefore, they're talking about the closed intervals. So if we take a look at 34, I believe. Okay, so 34 is g of x equals 1 over x squared minus 4 on the closed interval. They give you the interval is -1 to 2, right? So then they say, discuss the continuity of the function on the closed interval. So now we don't have a visual. We could graph this and come up with a visual. One of the things to think about with continuity and discontinuity with any function, if I gave you, let's say I just gave you a function not related to that at all, but 2x plus 5. Would you look at that and say continuous or not continuous? Yeah, continuous. If I gave you a function of f of x is equal to x over 4, continuous or not continuous? Continuous, yeah. So then we look at a function, f of x is equal to, let's say, x squared plus 5x minus 7. Continuous or not continuous? Continuous, okay? So then we're looking at, let's say, z of x, pick a different variable, but we have 1 over x. Continuous or not continuous? Not continuous. Why?
It's in the denominator.
Yeah, the denominator is causing the issue. So we know there's discontinuity at x equals 0. Now, if I said, hey, same function, z of x is equal to 1 over x, but I said, hey, closed interval from 1 to 5. Yeah, it's continuous, because it eliminates using the 0, which had the discontinuity. So from 1 to 5, it's no problem. So we come over here, that's what we're looking for, is thinking through, where is this going to be discontinuous?
2.
At 2
And negative 2.
and negative 2. So we know x can't equal 2 and negative 2. We look up here, is negative 2 included in our closed interval? 2 is, but not negative 2, but 2 is included, therefore, is this thing continuous?
No.
No. So they're just looking for you to discuss, and you would say something like not continuous at on the closed interval from -1 to 2 because there's an error at x equals 2.
Okay.
You could It's continuous from -1 to 2, but not on the closure. So not continuous at x equals 2. You could say continuous for, -1 to 2 open parentheses, that works, but not the closed interval there. Okay. So let me jump up, let's take a look at 30, we can take a look at, 35. It says, in exercise 35 through 60, find x values, if any, at which f is not continuous, which of the discontinuities are removable. So that's kind of what we were just discussing, got ahead of us a little bit. Like, if you look at number 35, 35 states for you, f of x, right, is equal to 6 over x. So this one says, discuss if there's any x values that are cause discontinuity. So what value causes discontinuity at 35?
0.
Yeah, x equals 0 for discontinuity at x equals 0. Now, find the x values for f is not continuous. Now what we know is, thinking about continuity uses, they actually don't refer to it as domain restrictions. If you'll notice, the three things of continuity was, it has a limit, it's defined, so actually that is actually a domain restriction issue, actually, that it's not defined there. So that is actually discontinuity at x equals 0 because it's not defined at 0. The other thing is the limit as x approaches 0 does not exist, right? Because, and you may not remember this, but the graph will look something like this. And so as they go, it's unbounded is what we say. As it comes to 0, it's unbounded, therefore there is no limit as well. So no limit, and it is not defined, using that word defined. So for that. So if you take a look at 36, which you have to do in your homework, removable, non-removable. Because we didn't discuss that for 35 here. Is this removable discontinuity? And we kind of discussed that briefly, and that is, if you can factor out the problem and cancel out the denominator, then you can think of it as removing the discontinuity. Here, you can't get rid of it, it's there, okay? So like on 36, you have 4 over x minus 6. Where is it discontinuous?
At 6.
At 6, is that removable?
I think so, yes, because you can multiply it by, is it conjugate?
No, but could you factor it out? Could you factor and get rid of, like when I say factor it out, let me just throw this over here. Remember, if you had something like x squared minus 1 over x plus 1,
Yeah.
it's not continuous at -1, but is that removable? And that is what we discussed. Yes, it is, because x minus 1, x plus 1 over x plus 1, you can remove it right there. So this function is essentially the same thing as this function, with the discontinuity though at -1. However, it's removable discontinuity. So in this case, 4 over x minus 6, non-removable. 37 is x squared minus 9. What do we have for, is there any discontinuity in x squared minus 9?
No.
Nope, no discontinuity. You can draw that whole thing. That I'm going to lift your pen. 37, that's it, 37, yeah. Excellent. What about 38?
It's continuous.
Yeah, it's continuous. It's just a parabola for those of you watching without a book. 38, which is f of x is equal to x squared minus 4x plus 4. So we can quickly identify that's just a parabola, and therefore anytime you draw a parabola, you never have to lift your marker off the board. You can just keep drawing, and so it's continuous. Okay, so that is a couple of those basic ones. We flip over the page, see if we get into something else like, okay, take a look at 40. Any issues at 40?
Yes, at 1 and -1.
At 40. At 40. 40 is what? 1 over x squared plus 1.
Yeah.
So f of x is equal to 1 over x squared plus 1.
Oh, plus 1, never mind.
Yeah, never mind. Yeah, so is there any discontinuity? No, no discontinuity. As now we get out something we can negative 1. There's no real values for that. So 40 continuous. What about 41? 41 is 3 minus, what is it? 3 minus cosine x? The trig review for Fridays.
No, is it 3x minus?
Oh, 3x minus cosine x.
No?
Now remember, sine and cosine have no undefined points. Tangents, secant, cosecant, cotangent, those all do. So sine and cosine are just going to be curves like this, right? Tangent, curve like this, curve like this. Secants, curve like this, you know, like that. So cosecants. So sine and cosines, no issues. So none there. If you look at, let's go with 43. So no issues there, but let's get to 43, see if we can generate some issues and talk about removable versus non-removable. This is f of x is equal to x over x squared minus x, is that right?
Yeah.
Okay. So continuous or not is the first question.
Say no.
Okay, we say no, not continuous, for what values?
0 and 1.
0 and 1. Okay, so at 0 and 1 it's not continuous. So then the question is removable or non-removable?
Non-removable?
Okay, you actually have a removable
Yeah.
and non-removable.
Okay.
So where is it removable discontinuity?
Oh, you can factor out. Yeah, factor out.
Yeah, so this actually can factor out. So it's
And that would be
removable
For 0 and
at x equals 0, non-removable at x equals 1. Yeah. Does that make sense there?
Yeah.
That one? Okay. So that's how you do a bunch of those. We can take a look at, let's look at an absolute value one. Absolute value ones tend to throw us off. Let's look at number 50. And 50 is absolute value of x minus 5, is that right? F of x equals absolute value of x minus 5 over what?
X minus 5.
X minus 5, okay. So we see variable in the denominator, so that's pretty easy, I think, to identify. Not continuous, right? At where? X equals 5, right? So, then the question is it removable or not? Tricky here because we want to say, oh yeah, those cancel, right? Or we may want to, but one's absolute value, one's not absolute value. So they're not the same function. First, like x, whatever it was, x and x was the exact same things. So is it removable or not removable? So with this one, it's going to be non-removable. So it's not removable at x equals 5 because they're not the same thing. You can't factor them and cancel them. Another thing is you can look at is there a is there a limit at x equals 5? x approaches 5, we have 3 ways to find limits, I believe. One way is graphing, good. Second way is algebraically, yep, analytically, algebraically, same thing. And then the third one is numerically. So graphing, we have the ability with graphing calculators to graph that, and then algebraically, there's no like cancelization that you can do. You can't just say, oh yeah, x minus 5 over x minus 5 cancels. So you can't plug 5 in, so there's no method there. So the only thing you could do then would be the graphing or numerical values, right? So if you run the process of the numerical values real quick, without making our math too difficult, right? So let's say you plug in 5 from the left-hand side. So that means, like, let's say you plug in 4, okay? So if you plug in 4, you'll get out positive 1 on top, negative 1 on the bottom. If you're plugging in 4, therefore you're getting out a negative 1, right? Now, that, obviously, 4 isn't really close to 5, like 4.9 would be, but we're just making, and we can do 4.9, you get out if you plug in 4.9, you get out a negative 0.1 over, I'm sorry, on the top you get out 0.1 over negative 0.1, right?
Yes.
Which gives you? Negative 1. Yeah, so that actually, our math is easy enough. What happens when you plug in 5 from the right-hand side? So if you plug in 6, let's say you plug in 6, you get out 1 over 1, you get out 1. If you plug in 5.1, you're going to have 0.1 over 0.1, which is 1. Well, you recognize they're going to 2 different things. Therefore, does the limit exist? No, therefore non-removable. Okay? So again, the idea of removable discontinuity is something that looks like that, like an open circle aspect like that. Because the limit exists as it goes to it, but you can factor something out. So that's another way you can check. I mean, and then we were like, oh yeah, I don't think we can factor because its absolute value is different than this, so it's not factorable, can't cancel, non-removable. Prove it with limit doesn't exist, therefore, it's a function that looks like, this, and whatever it might look like, I don't know, like this, 2 different things that it's going to. So. Yep, okay. I think that's going to take us right up to the bell. So that gives you a chunk of stuff. There's some on there like 63, maybe do calc chat for those ones. We can maybe discuss on Thursday if you're here, or Friday. Maybe Thursday I would just do some more examples if you guys aren't here. Make a short video so we don't get bogged down too much for the last little bit of stuff on 1-4 I should say. So we're on for, and number, you have to do 111 I believe.
Yes.
Yeah, that's challenging, but give it your best shot.
Okay.
Try to think through it. It's always a challenge for people, but
It's odd, so that's a good sign.
yeah, check Couch Chat and see.
I love that place.
Yeah, check and see what they have for you on it,
Okay.
and then we can cover it in class.